Hello and welcome to the walkthrough for tutorial 3. So let's just look at where to find it. If you go to app.navability.io, there is on the hamburger menu a tutorials page. This is tutorial 3 on insufficient data or underdetermined systems. We have a separate video that's a welcome that tells you a little bit of the context and the applications that are important. And then you can choose your own adventure. So there are multiple languages. In this case, all the videos have sort of different language choices. In this case, let's go with Julia as a 0 install, and let's use the CZJL version. See other videos for different languages. And if you hit begin, it'll spin up a notebook, a binder notebook. We have one already open, available over here. So in this video, we're going to walk through and discuss some of the main points for each of the steps in this tutorial. So the application focus is described in the welcome video. We're going to follow a range-only example here, where let's say there are Wi-Fi routers in the environment, and we're going to use the power level as a simulation for range. And then we're going to navigate some kind of device. Now we've put a little boat character here, because often underwater navigation uses acoustic ranging. So we're sort of playing both of those. But the idea is we're going to use range only as a motivational example. And what you'll see in this tutorial is when there are too few ranges. So in 2 dimensions, if you only have 2 ranges, you'll have 2 intersects. So just think about, let's say, Wi-Fi A and Wi-Fi C are working. You'll have a range arc and another range arc, and you've got 2 intersect points. So with only those 2, you'll have a bimodal result. If you bring a third, you'll have the unimodal result. So in this example, we're going to have a lower number of measurements and more variables that are weakly observed, and look at the non-Gaussian estimates that come out of that. We're going to build this in factor graphs. Note that all the factors here are going to have a Gaussian uncertainty, but because it's weakly observable, the posteriors that we estimate will be non-Gaussian. This is one of 4 mechanisms that we've identified how non-Gaussian behavior can enter a system. So the solver is open source, and you can have a look at that, and in that documentation we talk about the 4 mechanisms. So I'll just click through just to show. So there's the Caesar solver page, and into the documentation of that I'll just click over here. So you can read a bit more information there. And then in the introduction here we've got a link to, not there, but we have a link to the Caesar solver itself if you want to go have a look at that. Here's the source code, and the documentation takes you to the same place. Okay, so this example is mostly going to follow point 2, prior point 2, point 2.2 range, and then, as I mentioned, normal distributions only. So there are 4 beacons in the system, 4 landmarks. Landmark 1 and 2, we know where they are. Landmark 3 and 4, we don't know where they are. And we're only going to get range measurements from them when we're close enough. And the positions of our device that we're navigating will be x0, x1, x2 as we progress. So to simulate it, here's the ground truth data with the control interim running that. So this is in Julia. Julia uses just-in-time compiling in this format. This is more of a developer format. So the first time you run any code, it'll take a little bit of time to compile, but the next runs will be fast. And you can pre-compile, and we've got separate documentation on that. Let's load the libraries. We're going to suppress some printing. Rome is the library we'll use, which is under the umbrella of the Caesar packages, supported by NavAbility, and then some visualization. Just a note that if your environment doesn't yet have the libraries, you can use this to install inside. Once you've got Julia installed, you can use that. All right, so we're just waiting for this to run, as I said the first time. What we're going to do is we're going to create a factor graph. So we start with an initial factor graph FG, and then we're going to add the first robot position x0. And then also 3 landmarks as variables. So those are what we're interested in estimating, but there's no information attached to them yet. So after that, we will add 2 priors. So there, that's done. We'll add priors by add factor as a prior point 2 on L1 and on L2. So we know where these 2 landmarks are, and we're using the ground truth position for L1 and the ground truth position for L2 to pin them down with a covariance matrix of values 1 down the diagonal. So L1 and L2 are pinned with priors. Then the first pose, x0, will make 3 range measurements to 3 beacons, which are nearby, L1, L2, and L3. Now remember, we don't know where L3 is in advance. So there you are. So let's run that and then have a look at what this looks like. So we're just waiting for the code to compile the first time around. And then I'm going to just start the solve, so as we talk through the graphical picture or the graph visualization over here, the solve can start up ahead of us. All right, should be there soon. Just give it a second. Here you go. So we've added a factor. Maybe just a little bit on what information you're seeing here. So this is what the Caesar system provides. There's a timestamp of when it was added with time zone. The label of the factor, which was generated. It is a solvable variable. There's some details here. There's no multi-hypothesis in this. And then the type is a point two range measurement. That's this last guy over here. So that just represents, it's a range measurement from x0 to L3. Okay, and by that, there's the mean and the covariance of that measurement. So here it is. We've got x0 is the position, and we've got L1, L2, L3 as the three landmarks, and we know where L1 and L2 is, so they've each got a prior on it. And then these three factors, these blue dots, they're the range measurements. So to recap, there are 4 variables in here, and there are 5 factors. 1, 2 prior, and then 1, 2, 3 range relative factors. So priors represent absolute information, and these n-area factors represent relative information. Okay, the solve is busy progressing. Firstly, what do we expect to find? We'll talk through that in a little bit more detail, and then we're going to visualize over here. So in this graphical model, we've got 2 known ranges, so they'll intersect in 2 places. And then, so whatever estimate we have for x0, we've got a single range measurement to L3, so we're expecting to see maybe a ring around whatever estimates of x0 we find. So let's see if we see that. Just give it a second to complete. All right, so I'll just read here as well. Rome plotting is another package that provides visualization tools to draw the numerical values contained in a factor graph. There's a bunch of tools that help you with that. If you're busy running this tutorial in one of the SDKs, NavAbility SDKs, maybe Python or Julia, you will actually be visualizing using the NavAbility app. So you'd link out separately for that, but you'll see the same results, and the solver working through the data is the same thing. It's the CaesarJL solver on the inside. So as I said, this is the case if you maybe want to run the system locally and you want to do all that work in Julia, you're welcome to. There's a lot of information about using Julia from other languages, compiling binary files from it, etc. And we invite you to go look at the lots of content available online for that. All right, so here's a visualization of, maybe I should start the next one to also just compile ahead, of the 2 known landmarks, so L1 up here in cyan and L2 in black down here at 10, 25, or what is this, 30 minus 25. These are the 2 known landmarks, right? And then we had range measurements from those 2 landmarks, which we expect to intersect somewhere here between them. So let's have a look if we see that, and we do. So let's plot the belief on the first pose, x0. And we're saying let's look at contour plots with levels 5 confidence levels in red. So here we are. So one arc goes over here. The landmark 1 is up here, and landmark 2 was down here. So there's a intersect here at the bottom left, and there's a slightly smaller mode, but an intersect at the top right. Now every time you run this, you'll have a little bit of variation. So some of you might see maybe one mode captured here, but you'll see more modes develop later. Maybe you'll see 2 very well balanced modes. That's down to the stochastics of the solve, but the problem is weakly defined enough that more and more modes will show up. And what's interesting later is how many modes does the final solution have, and which, are you snapping to one mode, and how well can you recover from that? That's a whole discussion. So this is a pretty good run, so let's keep going. You'll see the static rendered images that are already in the notebook are the ideal sort of case. So next, let's look at what happened to L3. So if I just scroll back up, let me start that plot. So if you have a look back up here, L3 should be just a range based on whatever the estimates of x0 are. So let's see if we actually get that. And there we go, we do. So look at the scale, this is much bigger. So hypothesis 1 and 2 for x0 live over here, and around each of those we get this sort of donut ring. And those two donut rings are sort of falling on top of each other. They sort of narrowest over here and widest over there. So this is the computed result that comes out of the solve. So pay close attention. We're doing SLAM, we're localizing L3, and we're also finding, we're localizing the position x0. Then we're running a solve on the factor graph, and we're getting an answer back from it, which is this entire ring. Right? So this is a non-Gaussian marginal posterior that the solve is recovering. Right? So think about this carefully in contrast with Gaussian-only systems. Right? Even if it's mixtures, you might just have 2 modes or 3 modes. Here we're recovering a whole ring as a belief. So it looks simple, but it's an important distinction. All right, so if this was a Gaussian system, this would actually be, and you were doing it in matrices, this is actually singular. All right, so let's build a tool to have the robot drive around more. So, and this is entitled Gaining and Losing Modes, Various Hypotheses. So we're going to just run this helper function, which simulates the robot driving around based on the data we provided earlier. Okay, so this is the vehicle drives to function, and it's the just-in-time compiling that's talked about there. The exclamation mark, don't be confused by that. That's just regularly part of the function name in Julia. That's just a convention that we use to say, hey, this function might change something about the parameters being passed in. It's just a convention note to the user that this function will be changing stuff, and in this case it'll be changing the factor graph. It'll actually be adding variables and factors. So let's do that. So the vehicle drives from x0 to x1, and then the vehicle drives some more from x1 to x2 based on the data we gave it. And then let's plot what that new graph looks like. And then I'm going to go out ahead and also start the solve, and then talk about the picture as it comes out. So it's busy visualizing. There you go. Here's the new factor graph. So let's see where we can start. So x0 is over here, and we drove, there's the factor to x1, and then we drove, there's the factor to x2. And while it was driving, some of these posers were able to get range measurements from the different beacons, right? And note that L4 has showed up. So previously we did not have L4. So now we have L1 and L2 with priors, we know where they are. And L3 and L4 are the unknown landmarks that we're busy surveying in. L3 has 3 range measurements to it. L4 has 2 range measurements to it. And we're not quite sure how many modes are available throughout this entire system. So we're going to just visualize and have a look at what that is. So there, the solve I think is actually complete. So let's plot that. So the 3 poses, x0, x1, and x2, we're going to plot as red, green, and blue. So here you go. So here we're recovering, it's showing 3 modes over here. These 2 are sort of the main ones, and there's a little bit of probability available here. That's maybe a little parasitic or just like a little weak, but that comes out of stochastics. It's pretty close to what the value should be. So there's actually a whole mode that I'm circling over here and a whole mode over here, right? So as we run more of that, we'll see. But now look, x1 is in green, so maybe the robot traveled from here, 0, 0, where the mouse is. Let's just get the axis system in. So maybe we started at 0, 0 and drove along the x-axis to this position. Alternatively, we could have started up here somewhere, and the robot could have driven down to x1 at this lower position down here. And from there, the robot could have driven on to blue, that's x2, and the same on this side, right? So we're only plotting 5 levels. Let's maybe just make that a little bigger just to see what's going on. I'm going to say 10, just to get a bit more detail. It might get really busy, but there you go. So so there's a mode. So maybe the robot drove along this line, and maybe from position x1 it would have gone up to there, or to there, or to there. These are all different modes, different hypotheses. It could have also gone all the way down there. In the same, the robot could have started here somewhere, driven down from x0 over here, down to x1 in green, and then to any one of these locations for x2. So I'm just going to bring this back down to probably what you're looking at or something similar. Now remember, what you're looking at when you're running this might look a little different, but you'll have stochastically the same behavior. Okay, so we're just highlighting there are 2 primary modes happening. This one over here and this one down here. All right, so resolving the estimates to new beacons. What is happening with L3 and L4, right? So we have them in the factor graph, these two unknown landmarks, and we said there's 2 factors that range measurements that go to L4 and 3 that go to L3. So let's have a look at where they're at. And we're plotting them, L3 and L4, as pink and orange in this case. And look at all of these modes, so many modes. So let's start with pink for L3. So L3 could be here, it could be over here, it could be over there, it could be over there, over there. So let's just count modes that we currently see in this visualization. There might be small ones that we're not drawing. 1, 2, 3, 4, 5. So 5 modes are being recovered for L3. And for L4, oh my, 1, 2, 3, 10. Let's just say 10 or more modes are being recovered for L4. It might be interesting to just look at this as a higher level of granularity. Let's go 10 levels in the plot. There you go. So some of this is sort of more continuous and these sort of awkward odd shapes. So the distinction of using multimodal belief versus non-Gaussian belief, it's sort of in the noise of what you're trying to describe. But the point is that after the solve is completed, you're getting all of these various modes being recovered. So we don't quite know where these landmarks are yet, but at least it's more certainty than anywhere in the universe. All right. So the robot keeps on driving. So let's say we drive from x2 to x3 and then from 3 to 4. We'd make range measurements to the beacons as they're available, and let's solve that graph. I should have run that sooner, sorry about that. And let's plot and have a look at that. So this might just take just a moment to run through. While it does, let's maybe just keep this picture open so we can have a look at it. Right, so maybe I should just recap while that runs. So far, we don't know where the robot is traveling. We're from 0 to 50 up here to x100 somewhere, or whether it started up here off of 0 and is driving down to x0, x1, x2 to here somewhere. And why is that? I'm going to go further back, so just take this as a recap. We have 2 known landmarks, L1 and L2, and we got a range measurement from each for x0, and then we got a range measurement from each as we progressed. And we don't always, we only say within 150 units the range measurement is valid. But as you do that, you get, here's the one arc from L1, and the other arc from L2 is around here. And the 2 intersects are here and here. So these are the 2 sort of main regions. It's showing 3 now, but it's mostly this region and that region. And as the vehicle progresses, there's a limited number of options where it could happen. Now, what I didn't say before is the traveling of the robot is only a one-dimensional measurement. I should maybe actually highlight that clearly. When you're adding from x0, so from label to label, that is taken as from label to label. That is just taken as a point to range measurement. So the odometry in this case is a 1 degree measurement, or a one-dimensional measurement. So in the factor graph here, when you go from x0 to x1, that odometry factor between is only a range. You drove 10 units. The direction in which you drove is unknown. It's not a classic xy theta measurement, it's just a single range. What's the distance traveled? And the same there. So all of the blue dots you're seeing here, except the relative ones, are one-dimension range measurements only, and then xy prior and then xy prior. I should have said that clearer sooner, sorry. But I think now the solve should be complete, so let's go have a look. Yes, it is. And let's plot all the poses, x1, x2, x3, x4. There you go. So x0 is in purple. So the one mode, maybe the robot traveled from purple to red to green up to this gold color, x4, or the same the other way, x0, x1, x2. Here's x3. I don't see any x3 over here. It might just be low down. I'll plot in more granularity, and up here. So the major modes are here and then up along the x and then vertical, or start just off 0, drive down to the bottom left here, and then hook up slightly vertical on the left here. So these are the 2 main modes. Let's draw a bit more detail and see if we can tease out what's happening. I just want to see what happened to x3. It should be in there. It's maybe just a smaller mode. There it is. There's a little bit of potential. So maybe the vehicle drove from here at 0, 0 to x1 to x2 down here, and then up a little bit to there, right? So these are all possible hypotheses. Maybe it drove there, maybe it drove there. And the reason why there are so many is because the odometry is one-dimensional. Not two-dimensional, it's one-dimensional. It's just a range measurement. The other way is even worse. But there are overall there are two measurements, two big modes. One here starting along the x-axis, and one that sort of goes down to the bottom left over here. So two big modes because we only had two known landmarks. All right, cool. Let me see if I can run anything out in advance. I'm just going to run a little bit ahead. Let's do the drive some more and solve out ahead of us. Notice how even 7 new range measurements, the posterior on X3 has an increasing number of modes. So let's have a look at X3. So it's all of this, the bluish color. Right. There are many more modes, even though we're adding more data to the system, we're getting an increasing number of modes. So the uncertainty is growing faster, or the number of hypotheses is growing faster than the amount of data we're busy collecting. And again, every person running this will see slightly different results within stochastics, but something about these two dominant modes should be visible. Modes will be gained or lost based on the quality of the solve. We can turn the cranks up and solve more detail, it'll be a little slower, and the data that's being collected. Several parameters can be solved and can be tweaked for different situations. Certain applications will need different things. Get in touch with NavAbility with us. We can definitely help explain and help more there. Okay, the first robot position x0 and x1 also didn't change much. So we still have the two main modes here. Right, so even though we've been adding data and solving, these two modes are fairly stable, same with the x1 modes. All right, I think we just ran this now. So how are the modes doing for L3 and L4? These are the unknown landmarks. So it looks like there are only 4 modes now for L3. Previously we counted 5. There might be small ones that are not visualized. And I think L4 is becoming a little bit more restricted. Previously we said there's like more than 10 modes. Now there's maybe a little bit less than 10 modes, primary modes in L4. Just for interest's sake, since we're here, let's plot with 10 contour levels. Oh no, actually it's just these long streams that are connected together. Oh, I think I had the static image before. Yes, I think you saw what I was just describing was the static image in the notebook, which had a few more modes than what we're getting in this run. So that's kind of what the stochastic variation looks like. But the point is there's still multiple modes. And if you turn the granularity of the solve up, you'll recover more and more of them. All right. Oh, and it's after we've solved. So I showed you that's what happened. It wasn't the static render. It was the previous image. Then we'd already driven x5 and x6, which I ran just now and solved it. So this is the L3 and L4 estimate after adding poses x5 and 6. Sorry about that. Sort of step back. Let's plot all the poses. So we've now added x4 and x5, and we solved it. I ran that out a little ahead. Now let's look at all the pose variables. So there are, I think that's 7 poses so far. So what's happened now is we have still 2 modes potentially in x0, but it seems like we've dropped down to just 1 mode for the rest of the trajectory. So there's x1, x0, sorry, x1, x2, x3, x4 was up or down. X4 was out here to gold, then x5 is any one of these. So there's 2 modes over here, there's 3 modes in x5, and then there's this big blob here for x6. So in general, Solver has now picked, we're going down this hypothesis. All right. Accidentally, I described landmarks 3 and 4 already earlier, so I'll maybe skip that now. I'm just going to run the solve out a little ahead of us while we talk about this. So where are the landmarks? So L1 and L2 are 2 known landmarks. L3, we're saying there are 2 possibilities, and L4 has maybe 1, 2, 3, 4 modes sort of hanging out. Right? In your solve, you might see modes on the other side, or you might see many more modes. It depends on the stochastics of your specific solve. Okay, the solve is busy progressing. what I'm going to do now is I'm going to talk about the static image, and then we'll look at how close to that our solve currently just came out. So this image currently in here, well, so the solve is still going. The image you're looking at right now is the one that's committed to the repository. This one still shows for poses x0 through x8 two full hypotheses available. So maybe the vehicle drove from here in red, x0, to green x1, to blue x2, to x3 in purple, to x4 in yellow, to x5 in blue, x6 up here, where'd x7 go? I think it's that one. x8 is gray, so that's a long drive down to here, right? So maybe let's do that hypothesis. So there's one hypothesis which I'm tracing with a mouse now, up, around, and a square down to here, and then maybe one or two options. So that's mode, let's say that's mode 1, and down to here that's mode 3. But then there's also mode 2, sorry, that's mode 1, that's mode 2. So then mode 3 would be, let's start back from x0 up here, maybe we drove x0 in red to x1 in green to blue, x2, sorry, x3 in purple here, either to this mode for x4 or that mode for x4, so that would be maybe mode 3, that would be mode 4. So mode 3 would go up to this blue, mode 4 would go up to that blue. It seems like there's another option that's available here that's maybe just too small to draw, so that might be mode 5, right? Alternatively, we're starting to sort of converge back. So for x6, we have maybe mode 3 over here, mode 4 over there, but there's mode 5 and mode 6, I think. For x7, which is over here, they all collapse back down to 1. So that's interesting. By chance, x7 is a common point where these two mirror images live. So there's one image over there, and here's another image over there, and x7 just happens to be on that mirror point, and then down to those two modes. So we're tracking at least 5 or 6 or 7 modes. I've lost count now, but let's say there are at least 5, 6 or 7 hypotheses being tracked in here. So in our new run right now, let's see what we got. I'm sure the solve is done, yes. I showed you the static image. Let's actually look at the result that we got. So in our case now, we're just tracking one of these major modes. So x0, x1, x2, x3 would be up there, but then x4, there's one mode, 2 modes, 3 modes, 4, maybe 5 modes. From there we have to get to x5, so there's a main mode. Maybe there's at a stretch you can get back here. If we plot with more fidelity, you might see more things show up. So in this run, it looks like the solver has fallen to one of the major modes, and it's tracking some of the modality within that. So here's another small mode over here. And I'm expecting that as different folks run this, what you'll see is some folks might just land on that mode, or this, in our case, we're landing on let's say the left mirror image or the right mirror image from those original L1 and L2 cases. All right, so let's just trace it out one last time. So x0 in purple, x1, x2, x3, x4, but there's 2 other options, x5, x6, 7, and then 8. There are 2 options here as well, as the static image had. And at this stage, the solver had lost this mode. It might recover it in the future based on information we're not sure. Right, and part of the work that NavAbility is doing is making these solves more reliable, more robust, and faster. So tune back in the future, and hopefully what you'll see is a very consistent, high-quality result, always. All right, so where are the landmarks? Landmarks modes have now reduced down to unimodal on 3 of them and 2 modes on L4. So that's pretty interesting. So there's L1 and L2, which we knew in advance. L3 has been localized, L4 and L5, and it's localized to this one hypothesis. So I would also add, based on the fact that we had 1 mode versus the 2 mirror images, is that this problem is designed to be as loose as possible. In reality, you'll probably have more information. We're really stretching it. If you just use wheel encoders with XY data for odometry, you'll have much more fleshed out results. So this is just meant as an example in extreme. So here's the final factor graph. All the blue dots are range-only measurements, except for these 2 priors, which are where L1 and L2's priors go. That's an XY prior and an XY prior. So you've been solving factor graphs where you got non-Gaussian estimates coming back on the variables after the solve. and that it's non-Gaussian because you can't. The belief here isn't just a single unimodal belief, right? It's got all these funny shapes to it. So this is an odd shape. These are odd shapes, and there's multiple modes. The mass is sort of really spread out, and that's a pretty cool thing. So here's a question at the end. Theoretically, should there be one overall trajectory hypothesis, or should there be two? I'll answer that by saying there should be two, because we only had two fixed pieces of information, and the one trajectory option was to drive this way around, or the other trajectory option was to drive down to the left first. In our video recording now, we got the left one first. In the static images for this tutorial, you'll find that that run showed both hypotheses exist. So read the static render of this, and you'll see the two modes case. There's more information. Any questions, any concerns, any comments and feedback, please post them. You're welcome to post in our Caesar documentation, or just reach out to NavAbility on the Slack channel. So I'm just going into the documentation here. Welcome. You can find the source code, or you can join us on Slack. So let's maybe go to the source code. Feel free to open issues, discuss with us, or join our Slack channel, which you can find a link for over here, or go to the NavAbility website. And in here, welcome to ICRA, you can join, you're welcome to reach us and connect to us anyway here. All right, that concludes our example for today. Check out the other examples. Tutorial 1, 2, 3, 4, 5 are also available and will be linked. Thank you.